let's transit to our lecture today on distributed software systems architecture, and the topic today would be about service-oriented architecture and RPC services. So before we start the description of what service-oriented architecture is, it would be nice to remember what was the way of the technologies that brought us to the current place, to the current positions. So in from the 1980s, we started the development and forming of the client-server model, and first networking equipment started to arrive that allowed to connect not only the mainframes, but also small and small size computers. So client server technologies arise, and Berkeley University developed the basic standard for organization of the distributed systems and network communication that they called Berkeley sockets. They were developed in 1983. So, as we remember, using Berkeley sockets, it is not the most intuitive way to organize the communication between the client and server, between the distributed systems, because they work as a stream of bytes. And the developer should think for themselves how to serialize and deserialize the information, how to encode the information inside this stream of bytes. And it is not always useful just to send stream of bytes. There are a lot of examples when you want not to have the stream of bytes, but you want to call, for example, a remote method. So when you're calling remote method, you usually would like if the system would take care of how do you process the calling of the remote procedures. So first, RPC systems started to arrive in the 1985. Also, using RPC, it is not the best and not so convenient way to organize if the system is developed on the basis on different languages. So if you have one platform that is developed on one language and the second platform is developed on the second language or the second system, there is no standard way to organize the communication between these two platforms. So the Corba technology arrived in the beginning of 1990s, a common request broker architecture. It is a platform that supports communication between two systems or between several systems that are developed on the basis of different languages. So one of the components could be developed using Delphi, the second component could be developed using C++, and they could communicate with each other using this Corba infrastructure. And that system was very, very popular in the 1990s, but the problems with the huge and complicated standards, it leads the way of this technology to its dawn. So right now, no one uses the Corba, just maybe some small amount of legacy systems. In 1995, new age of technology started to arrive. Java took over the world, and they developed their own way to organize communication. They called this Java Remote Method Invocation. So when you use Java on the client and on the server, on all the sides, that's great that you can use remote method invocation, and if you use only Java, that is good for you. But what if you use different languages? What if you would like to communicate through the internet, because Java remote method invocation work very good in the network, inside the local network, LAN, but when you go to wide area network or the internet, you have a lot of problems. For example, most of the times, the client and the server would have only limited amount of ports open to access, to accept the requests. For example, HTTP ports. As usual, if you install the HTTP server, you as administrator open HTTP ports like 80 and 443, and you close all the other ports because you don't want security holes in your systems. So that issues led to creation of services and web services, and especially XML Web Services, or another way to call them SOAP Web Services. The standard of SOAP Web Services was presented by Microsoft and their partners in the beginning of 2000s, and this standard was based on the XML language that was very, very popular those days. And even today, XML language is very popular to describe data information, data-specific information, because it is a very well-structured language. And all the 2000s, from 2000 to 2010, SOAP Web Services was the best way to, and the most standard way to organize remote communication in the distributed systems. But 2005, another approach appeared, and this approach is called REST. And we also would take a look about this approach and about these types of services. They're different from the SOAP Web Services, especially because SOAP Web Services, most of the time, they describe the remote procedure call operations. But REST services, they most of the time describe the working with the remote resources. So this is about action, and this is about the state management. And there are more differences in the SOAP Web Services and the REST, and we would take care about this on our next lectures. So 2010, the main advantage that we got in 2010, and that we're living with this advantage till now, this is clouds. Cloud computing systems, they arrived very quickly, and today I think most of the internet using cloud systems that way or another. So we would discuss what cloud computing is, how it works, and how it influences working with the distributed systems. And because cloud infrastructures arrived, a lot of systems started to be more finely granulated on very, very small services that work with each other using this infrastructure that provided by the clouds. And today, this architecture is called microservices architecture. And during this course, or in the next semester, as the next part of this course, we would deeply discuss the microservices architecture and how it is different from the approaches that was before. So now we see this timeline, now we see where we're standing. So we are starting from this part. We would start to discuss our service-oriented architecture from the concept of RPC services and SOAP Web Services. But before we start, I would like to introduce you to the Jeff Bezos. So Jeff Bezos is the most, right now I think he is the most rich person in the world. But I don't know if he is the most, but he's one of the most rich persons in the world. And he is CEO of small bookshop that called Amazon. And In 2002, you can see it here, the Amazon was not this giant as it is today. In 2002, Amazon was a web shop and nothing more. So Jeff Bezos, as a great entrepreneur, he understood in 2002 that internet shop is not the only commodity that he can sell. He understood that he can sell sell to the customers not only the commodities from the shop, but the shop itself, the internal parts of the shop, how it is organized, how it is working. So he wrote this letter to the uh, developers and the managers of the development teams in his Amazon web shop. First, all teams henceforth expose their data and functionality through service interfaces. Teams must communicate with each other through these interfaces. There will be no other form of process communication allowed. Direct linking, no direct reads from another team's data store, no shared memory model. The only communication allowed is via service interface calls over the network. It doesn't matter what technology you would use, HTTP, Corba, or etc. But now we know that HTTP won and Corba lost. But never mind, that was 2002 and today is 2020. All service interfaces must be designed from the ground up to be externalizable. That is to say, the team must plan and design to be able to expose the interface to developers in the outside world. No exceptions. Anyone who doesn't do this will be fired. Thank you. Have a nice day. This was the groundbreaking letter and understanding of what the architecture of the system should be. You know, previously, and we discussed this previously, the architecture of the good system was the layered architecture. So we have the incoming request and we have the user interface layer that works and communicates with the application logic layer that uses the data from the data layer, as you remember, to store and process the request. And if we have a big web shop, for example, internet shop, we have a part, for example, this is a part for the consumers. This is a part about the products. And we have a huge database here on the data layer that works as a common intermediate layer for communication between all the other layers above it. So we have a huge database, and the application logic about the consumers and the application logic about the products start here. So if we want to have information about the orders, that is the connection between the consumers and the products, we create a table that links consumers and products, and we call it orders. So the application logic of our system maps to the relational database on the data layer. And this relational database works as an intermediate logic and intermediate language of our system. So request goes here, it passes through all the layers, we work with the data, we process the data, and we provide the result of processing of this request. So that is very good when you're working on some small internet shop, when you have a team of designers and developers, about 10 people, 20 people. You can manage the organization of development of these small, as we call this, monolithic application. This is monolith. And when you work with the monolith, and if it is not a huge distributed system, it is good because it is easier to organize the communication between the layers through the common database and through direct reads and writes of the tables of this database from the application logic layer. But let's imagine that our system start to begin to being bigger, it expanding. We have not 10 developers that works in this system. We have 100 developers. And these 100 developers, they are divided to 10 separate teams. And one of the teams working on the project about the consumers. The other team works on the project about the products. The third team creates authentication services. And these teams, due to this architecture, they should share the same data layer between them. And they should discuss with each other when they want to pass the new feature, how would we organize working with this feature on the application logic layer and on the data layer. And if the negotiation fails, the feature would not come easily. The feature would be lost. And the communication between the teams would be very, very tight. The authentication team should work very, very tightly with the consumers team and with the products team and with all the other teams to understand how this system would work with each other. And that was the problem before this letter. As we remember, this was the Jeff Bezos letter in 2002, and he said that now we would not use this big monolithic system. Each of the functionality of the teams, so you see here that he places the teams as a key element of the piece of the infrastructure. And they should export their data and functionality through the service interfaces. So now we have consumer team. We have products that we sell, the products that we sell to our consumers. We have authentication team or authorization team, okay? And previously, they worked on the same layer of the data layer with the same database, but now they should expose their functionality through the interface, that is consumer interface, that is the product interface, that is authentication interface. And now they would not be able to read directly, because you can see here right now they start to have their own data storages on each side of the teams, because they need to store the data somewhere, but they're not allowed to share the direct connection. So the authentication, for example, the consumer team, it says to the authentication team, okay, I would like to take the data from your data store about the logins and the passwords of the users. And authentication team would say, no, never, you would not do this, because we are not allowed the direct read of the data between different teams. So the consumer team says, oh, what should I do? How can I take this information? And the authentication team says, we exposed this feature in our interface. You can ask us. And through this interface, we would go and we would take the information as we want from our data, and then we would give this information back. Why is it different? Why this approach differentiates from the approach before? We just add another layer to the communication. We just add one more step. So this step is very crucial, because there can be some example when the authentication team decides, we do not want to use this type of database. We would like to use external somewhere in the internet authentication server. For example, we would allow the authentication of our users via the Facebook. So right now, when you go to almost any service you want to authorize, they would ask you, would you like to authorize using Facebook or Contact or Instagram or any other service or the social network that you use? So if the consumers team takes the data directly from the database, from the authentication service, this feature would be very hard to implement. But because the authentication team create their interface, now they can pass through this request as they want. For example, directly to the Facebook. And the Facebook would give them the authentication credentials that they would pass to the consumers team. Because we have this abstraction of the interface of each independent team functionality that they provide, now we can divide the structure and the architecture of our system to the set of independent services. So this is a very crucial part. This is the diversification between the monolithic, or someone calls it the silo approach of the distributed system, that you can see here. It is the three-layered client-server architecture that we discussed on our previous lecture. We have user interface, we have data processing, and we have data storage layer. And the service-oriented approach, when each part of the functionality of the system is encapsulated into a separate service, and this service can work with his own database and should work with his own database, and this service does not allow direct reading or writing of this data because it provides this great interface to work with. So right now, external user can use this service as his own feature on his own website or in his own application if this web service designed from the very beginning to be able to be used as for the external developers in the outside world. So there is another way to see this structure, and this is very nice picture that I found. This is the evolution of the software architecture. I don't really think that in 1990s all the architecture was spaghetti oriented, but I think author knows the best. But what I truly agree is that in the 2000s we have lasagna oriented architecture when we had this huge monolith and we had layers in this monolith. You know, lasagna, it is part of meat and part of the intermediate part and another. So when we have this lasagna oriented architecture, if you cut lasagna, all the internals are going outside. And that is the silo approach, monolithic approach, or this three-layered client-server architecture. And in the 2010, we started to warp this lasagna into smaller pieces. Inside this piece, we still have the same data, but now this data is not shared between all of the monolith. This data is inside the small piece of the service. And these guys, they call this ravioli-oriented architecture. So ravioli is like lasagna, but very small, and it has specifically designed interface so they can be consumed one by one without problems that the internals would be on the plate. So this is the age and this is the approach that we are discussing today, and this is the common differentiator between the service-oriented architecture and the monolithic architecture. The independence of the services is the crucial role to organize the distributed system in the current age. So we successfully passed through the introduction, and let's go to the more formal definition of the service-oriented architecture of the distributed systems. So by the definition of the OSS, or Organization for the Advancement of the Structured Information Standard, the service-oriented architecture is a paradigm for organizing and utilizing distributed capabilities that may be provided by various owners. So what it actually means is what I described previously, that the components of the application right now, they act as interoperable services, and they can be used independently. Moreover, you can recombine the components between the other instances of the same components that provides the same capability. For example, you can create an application that would provide you recommendations about the physical activity that you should take today. So, for example, do you need to run? Do you need to swim? Do you need to jog or any other type of physical activity skiing, yes. But to understand what types of activities are available to the person, you would like to understand what is the weather today and the region and the geoposition where the person is located. So you don't want to create your own weather forecasting system. So you include the service functionality of the weather forecasting system in your application. You call the weather forecast and you tell them the name of the city where the user of your application is located, and the weather forecasting service would give you back the forecast. So, for example, tomorrow would be plus 10, plus 15. So I would recommend you jogging because it is good for your health, and the weather would be great for jogging in the current conditions. Okay. And you create this application and you use the functionality of this service as an independent component of your system. But in several weeks of testing, you understand that this weather forecasting system, it is good, for example, for China, but it provides very bad results for Australia. And now you think, oh, what should I do? How can I fix this problem? So using service-oriented architecture, you can fix this problem very, very easily. You can still use the web service 1 in the conditions where the user is in China, but you can find the web service 2 that would provide you better results for Australia. And if the user is located in Australia, you would ask another web service for this weather forecast, and this another web service would give you the results back. So these web services would be able, you can substitute and recombine these web services to provide the best quality of service to your users. When we are discussing the web services, we should mention that there is not the one type of API that you can use when you create or when you use the web service. Currently, we can highlight these four main styles of web services APIs, and we would discuss these styles consequently in our lectures. First, it is RPC API. You know about this API very well. You used this already, and you had the description of this API on our previous lectures. When clients, what the clients want, they want execute remote procedures using the HTTP protocol. And the web service API provides, the RPC API provides these capabilities. The second type of the API that we would discuss, it is message API. So the message API, when you use the message API, you try to find the solution to the following question: how can clients send comments, notifications, or other information to a remote system using the HTTP without binding themselves to the remote procedures? You know, when you use remote procedure call and you divide your functionality of application to a big amount of very small procedures, your interface become fragile. If you change the interface of only one procedure, all the clients should rebuild their client versions of your web service because the interface changed and they do not know how to use the new version of this interface. So Message API tries to solve this problem. The third way of the API, it is about the Resource API, or how a client manipulate the data provided by the remote system using the HTTP without linking itself to remote procedures and without having to create a special problem-oriented API. So RPC API and the Message API, mostly they encapsulate the procedure, they encapsulate an action. But there are a lot of cases when you do not want to create actions. You want to create resources. You want to manipulate the data. You want to create resources, edit resources, read information. So Resource API provides you these capabilities. And today, mostly Resource API implemented using REST. And the fourth specific style of the Web Service API, it is Graph API. The Graph API, it is the most recent development, and the Graph API answers the question, how do I generate a query for a graph of objects available on a remote server by requesting specific fields that the client needs to process. So the Graph API is an extension of the Resource API, but it is very specific to the current state, for example, of the social networks. Because if we want to create a client for a social network, for example, for a Facebook, then it would be very hard to create a resource for each of the elements of the Facebook social graph, because there are so enormous amount of the elements that are interconnected. The user has the user has a tree of their friends, and each of their friends has a tree of has a list of the posts or the news or the pictures, and each of the posts has a list of comments, and each of the comment can have some people liked this comment or they commented on the comment. So you can see that this structure start to expand very rapidly for each user. And if you would use Resource API, this would be very hard to create the queries to this structure. So the Graph API provides these opportunities, and we would discuss it in the next lectures. So let's start from the first API that we described here, the RPC API. So the RPC API, to implement the call of the remote procedure using the HTTP, well, it is necessary to identify how would we describe the remote procedure, how would we describe a set of elements that we need to send to this remote procedure to get the results back, and how we would describe the results of the implementation of this remote procedure. And we need to understand where this remote procedure would be located. But because right now we're using HTTP to define the location of the remote procedure, we can use simple URL or URI to execute this procedure. So When we implement the remote procedure call using the RPC API, we would implement the following process. The client sends request to the URI of the remote procedure service. And in this request, we would provide this information. We would provide information, the procedure name, what would we like to execute on the remote server, and call parameters. What would be the parameters of the execution of the remote procedure? We send this message to this URI. It would be processed by the server. The server would choose the service that would implement the request. And when the procedure would be implemented, the service would send back the results of the processing of this procedure. And the reply message would contain the results of the procedure execution to the client. So you can see here that the schema that we designed here, that we draw here, it is not different from the standard remote procedure implementation that we discussed before. The only difference here is that we use URI and HTTP protocol to organize the communication, and the communication is based on the HTTP protocol. So previously, as I mentioned, we could implement this type of communication using a low-level transport protocol, for example, BSD sockets API. But the main issue of the organization using this low-level protocol is that developer of the system should take care for themselves. How would they organize the data transformations between the clients and the servers, especially if they were implemented using different languages or different platforms? Because these different languages or platforms may use different data encoding methods. So actually, using the BSD sockets was the main problem that the main problem of the BSD sockets was that it would be very hard to create clients and servers using different protocols and different platforms. Corba and distributed COM technologies offered some solutions to this problem, but they did not solve the problem to the very end. Especially, they did not provide the transparent messaging over the internet, because often all the ports on the firewall of the server or in the client, they were closed except the HTTP ports like the port 80 or the port 443 to accept and organize the communication using the HTTP connections. So the use of HTTP protocols solve many problems of data exchange and transition. It allows clients and servers to communicate based on different platforms. They communicate over the internet using the common media of the HTTP protocol. And the HTTP protocol, as we know, it is text-based protocol. So there are many implementations of RPC, the HTTP right now on different languages. It is just JAX-VS on Java, Windows Communication Foundation on Microsoft.NET. They allow you to create simple web procedures and clients to them without having to understand the data formats like XML or JSON, encoding methods, or service structure descriptions. And during these lectures, we would describe two types of the implementation and approaches to the XML Web Services, to the RPC services implementation. First, it is so-called XML Web Services or SOAP Web Services. This is the most standard approach for the implementation of XML Web Services that uses Web Services Description Language, or WSDL, and the SOAP protocol to organize the communication between the services. And there is a big set of standards and rules that organize this communication, and we would cover this in our next lectures. Another way to organize it is non-XML or not SOAP Web Services RPC. This is a range of different RPC protocols such as gRPC, gRPC using HTTP 2.0, I think. So JSON RPC that uses the HTTP as the basis for the organization of the communication. Oddly enough, XML RPC, it is not SOAP Web Services, so it is also a different approach to organization of the RPC via the HTTP. And we would cover the JSON RPC also in our next lectures. So to get to the description of what types and how the RPC is implemented via the HTTP protocol and the RPC web services are implemented, we would need to describe the components of the service-oriented architecture. So to describe the service-oriented architecture, we need to define what are the service components of the services. We need to define what are the service contracts or interfaces. We need to define what are service connectors or the transport of the service-oriented architecture system. And we need to define what are the ways to discover the services that are already implemented and available, the service registers. So service components, they provide transparent network addressing. Services they use standard HTTP URIs to address each other. And services are open, self-defined components that support rapid construction of distributed application. We would talk more about the self-defined components later when we would describe what are the contracts of the services are. Here, what can I say is that services can be fine-grained and coarse-grained. So the difference between them is that the fine-grained service provides elementary volume and functional load, and it ensures a high degree of reuse. And to organize the implementation of the specific system, you must coordinate or orchestrate the work of several services to get the result. This is the most common way to organize the work of the so-called microservice systems, where we have a set of small services, and to organize the implementation of some kind of work, we need to orchestrate several services to work as one big orchestra to implement the functionality that we want. Coarse-grained services provide high degree of encapsulation of functionality. It is easier to implement if you had a big monolithic application, and now you need to move from this big monolithic application to the service-oriented architecture. You can start cutting the monolith to big services that encapsulate the internal part of the functionality, but you are not ready to go fully to the service-oriented architecture part, because then you need to rewrite your system from the very beginning. So as possible example of this coarse grade service, you can see that this is a service to solve the quadratic equations, and we send this request to this service, and then we get response from this service. And this service encapsulates all the functionality, how it works inside this service. And if we're going like to the very fine grained, of course, this is very extreme example, and no one implements it like this in the real world. But to understand the picture, let's try to divide this service of the quadratic equations solvent to more specific services. For example, we can implement the square root service, the multiplication service, addition service, division service, squaring service. And to solve this equation, we need to orchestrate the work of all these services together, so these services provide you the result that you want. Of course, it is not necessary to show all of these services as open services to the other world, but you can develop each of these services by the independent team on the independent language. They can be hosted on independent software systems. And if somehow we figured out that the multiplication service, it is much more needed than, for example, division service, then we can have not one instance of this service, but we can have a set of multiplication services that would distribute the load when we need to solve a big amount of quadratic equations. So the request would be given to one service at a time, so we could scale the functionality of our system using these fine-grained services. But of course, we would take much harder to implement this orchestration of independent services comparing to the effective and orchestration. It is not needed to the coarse grade service in this case. Second part of the service-oriented architecture, it is description and definition of service contracts. The interface of the service is a description of possibilities offered by a particular service. It is defined by the service endpoint address. Where should we call, where should we go to ask this service to provide us some capability. Second, we should describe all operations provided by the service. What can we call from this service? All the messages supported by each operation. So what are the parameters of the call that we should pass so the service could interpret our request and give us a response? Rules and characteristics of the service and its operations. So here we can see that on this slide we defined the endpoint where the service is located. We defined all operations that are implemented by this service. We defined all the parameters of these operations, incoming and outgoing parameters of these operations. And we defined the means of transport that this service accepts. For example, here we say that we use HTTP and the SOAP. Here, these are two messages. The input message would be one parameter integer, and the output message would be one parameter, integer, and this would be the method, for example, added. Okay, input would be two parameters, two integers. Okay, add A and B. And here we say that this service is located on the address http myservice.com. So if we would give this information to the client, our client would know that he would need to go to this URI. He would ask this service to implement this method, and the parameters of this method, he need to send two integers to the input, and one integer he would get as the output, and he would use the HTTP SOAP to organize the communication. So if we would give our client this description of the service, that means that the client would be able to call our service without any issues. So that is how the interface should be defined of the RPC web service. Third one, it is service connectors or the transport. As I just described in the interface, we should describe how the exchange of information between the components is organized. If you use flexible transport protocol for the exchange of information, it improves the software capability of the service-oriented system. Going back to the transport that we use, if we use some open standard transport means, for example, some protocols that can be implemented on different platforms like JSON or XML over the HTTP, then we would say that it is very, very easy to implement the capability to exchange the data and the requests and response between different systems if they use common intermediate languages and formats. So the last part of the service-oriented architecture, it is service discovery mechanisms. So we should think about how our system would be able to tell other systems that these services are available right now, and these services, they were already developed in the infrastructure, and that you can use their capabilities to implement your own services. So there are different ways to organize the system service discovery. Static discovery focuses on storing information about rarely changing systems. For example, such approach as UDDI, you have a big register of the services, and UDDI stores this information, and it can give you back the description of the interface of each of the services that are available right now in the register. So the second approach, it is dynamic discovery. Dynamic discovery is an approach that you have no some regular one storage system or catalog, but there is a huge amount of services that are going in and going out from time to time. So peer-to-peer systems or mobile agents, they use this approach to organize the discovery mechanisms of the system. So yes, let's go to the main principles of the RPC services design. So first principle of the RPC services design is that the services, the RPC services, they encapsulate actions, not objects, not resources. So when you divide your system into a set of independent RPC services, you should understand that inside these services, you should think about them as a part of the process, not a part of the data division. So each service should be encapsulating some domain logic part. Next thing that I want you to understand is the cohesion of the software system. And we talked about this several times before, that we should think about the system's cohesion as a degree of knowledge and dependence of one object or component from the internal contents of the other object or the component. And we can divide the systems on tightly or strong coupled systems or loosely coupled systems. So services and service-oriented architecture should be developed as a loosely coupled system. How do I describe this thing? So tightly coupled systems or tightly coupling occurs when the dependent class or object contains a link directly to a specific class or an object that provides the same some capabilities. So here we see the class that is connected with another class, with a device, and the tester class, it knows about the public capabilities of the device class. That's very good if you create very small system and you do not plan to make this system scalable enough. But if you would like to create a tester for different types of devices, then you should not link this tester class to the device 1, device 2, device 3, device 4. The better way to organize this connection is to create a device interface. And loose coupling occurs when dependent class contains a reference to an interface that can be implemented by one or more specific classes. So now the tester class, it knows information only about the interface, not about the implementation. So how we implement this interface, it is a problem that is solved by each class that implements this interface separately. So now the tester, it should not know about the direct implementation of the device interface by the DVD player. We just know that DVD player implements the device interface. So we can create a tester class that would be universal for the DVD player and CD player. So a service system is loosely coupled if a service can acquire knowledge about another service remaining independent from the service's internal logic performance. So here we have service 1, we have service 2, and they are connected using the interface that is provided by the service 1 to the service 2. And if service 2 implements its own interface like this, implementation 1, it is good. But if the team of the developers would decide, if you remember in the beginning of the lecture, we described how authentication team, they decided that they don't want to create their own authentication service. They want to use external one. So here it is example when you can use some other implementation. This is implementation 2. And if the interface stays the same, that means that the service 1 would be able to communicate with the service 2 the same way it communicated before if the interface stays the same. This is interface, this is implementation. So if the implementation changes but the interface stays the same, that means that service 1 can communicate with the service 2 using the same protocol. That is the advantages of loosely coupled systems. The loosely coupled approach decreases the number of relationships between the components of the system, and it is possible to increase the working system by creating new classes with a single interface. So now we have the interface, now we have class 1, now we have a set of classes that implement the interface, and in the number of connections here, it is clearly less than if we would connect each of the class directly to one another without the common interface. And the implementation of the common interface allow us to decrease the amount of connection between the elements of our system. Third principle, services should abstract internal logic. Every service should act as a black box. It should not reveal how it is implemented inside. The service should hide the implementation details from the interface that it provides to the world. That allow us to change implementation details when we would feel it is necessary. You should not expose what databases you use, what data fields you use, what is the specific ways to implement the logic that you expose in the interface. The interface should be as clear as possible without the implementation details. Next, services should be autonomous. You should remember this from the Jeff Bezos letter, that there should be no other way of communication between the teams just using the service interfaces. So we have service 1, we have service 2, and we have a set of resources that are allocated to the service 1 and the set of resources that are allocated to the service 2. So if the team of the service 1 would like to get something or would like to put something into this database of the service 2, they are not allowed to go directly to this database. They should instead ask for the service 2 to provide this interface, and they would ask this service 2 through this interface to get or to set the value they want, and the service 2 itself would implement this feature and would get the service 1 the result. There are two types of autonomy that we can implement. The first one, it is weak autonomy. Autonomy. It is that service level autonomy. Service boundaries are separate, but they can use the shared resources. Do not use this type of autonomy because it is very easy to break this system then. The best way of organization of autonomy, it is pure autonomy, when business logic and resources are fully controlled by the service. So it looks like this. When we have the second service here, the second service should use this interface, and the service 1 would pass the requests to the elements, to the internal parts that it feels necessary to implement the request of the second service. No direct connections whatsoever to the resources that are inside of the service. And the last principle that we would describe today is that services should be stateless. Clean services, they significantly limit the volume and the time of information storage. it is the most often said that service is stateless if all the information required to the service to implement to implement its procedure is stored in the request from the user. So here we can have two types of services. First type of services, they receive the procedure call and using the parameters that user provided, the procedure of these parameters A, B, C, and D, this is the function of these parameters A, B, C, and D, and that's all. So the user one, he sent this request to the service one, and the response of A, B, C, D would be the answer of A, B, C, and D. If the user 2 sends the same request with the same parameters, procedure A, B, C, and D, to the same service, the second user would get the same result as the first one. So if the users, they passed the same parameters to the service, they would get the same result. That service we call stateless. That means that there is nothing inside the service beyond the parameters that provided by the users. And this service is very good to implement because we can scale this service very easily. We can make this service on one server, another instance of this service on another server. We can have 10 instances of these services, and no matter what instance of the service the user would call, he would get the same result. And that is the best way to organize services in the stateless manner. The stateful service, on the other side, it is very, very different. So if we have the stateful service and the user sends us a request A, B, C, D, the stateful service would get the user the answer that is based on the parameters of the call, but also on some hidden state information about this specific user that is stored inside the service. So the service 1 would give the user 1 answer 1, and if user 2 would call the same service with the same parameters, and the service 2 would have some internal information about the user 2, he would use this information and he would provide this user the response A2 that is different from the user's response for the user 1. Let's consider this very simple example that we described previously. Stateless, it is like remote procedure call, RPC. And stateful, it is more about like remote method invocation. Because when we work with the methods, we work with the state of the remote system. And when we implement the method, we coordinate the implementation of this method with the state that is connected to a specific user on the system. For example, when we add some product to our product cart on the internet shop, so please put the new product in my shopping cart, and this is the same request. User 2, his shopping cart would be very, very different from the shopping cart of the user 1. because they have different state of their shopping cart previously to the implementation of the same request. So this is the stateful approach. And when we implement the stateful approach, we have some problems because we cannot easily implement this. We cannot easily implement scalability because without the knowledge of the state, we cannot just copy the service to the service 2. We need to put the state on the service 2. So the service 2 would easily implement the same request to the user 2. So if you are able to implement stateless services, you should implement them. Stateful services are harder to manage, harder to scale, and you should use as small amount of user information as you can in your system. And on the conclusion, I would like to say that in this lecture we discussed the service-oriented architecture, that it is a paradigm for organizing and utilizing distributed capabilities that may be provided by various owners. And services themselves are open and self-defined components that support rapid construction of distributed applications. We discussed key elements of service-oriented architecture, including service components, service contracts, connectors, and discovery mechanisms. And we discussed the main principles of RPC services, that RPC services should encapsulate actions. They should be loosely coupled. They should abstract internal logic. They should be autonomous, and they should be stateless as far as you can implement them. So this is the conclusion of my lecture today. I hope that you liked it, and please be safe in this time, and see you next week. Thank you very much for your attention and participation in the lecture. See you. Goodbye.